we'll look at applications of that, and I will try to see how well we can estimate this transformation. Sorry, it doesn't work. Perhaps I can come here.
No, that's okay. I think it's. Does it work now?
Yes. Okay. So just a quick review of the mutual information. Suppose that we have vector random variables x and y, and characterized by a joint PDF f of x and y, marginal density f of x and f y respectively. Then the mutual information between the two vector random variables is the expected Kullback-Leibler divergence between the joint and the product of the margins. So that's what it is. So it's this measure of dependence, which has certain nice properties. So for instance, it's non-negative, of course. It's a symmetric function of x and y. And it's zero if and only if x and y are independent. Otherwise, it's non-negative. It's positive. Then it's invariant to one-to-one transformation of y and x. And it's related to entropy via this relationship. So the mutual information is the marginal entropy of y minus the conditional entropy of y given x. Or you can reverse the role of x and y here. This is an equivalent formula, and so on and so forth. So this measure of dependence is non-negative. You can convert it into a measure of dependence between 0 and 1 by taking the mutual information index, which is this transformation.
This measure symmetrically with x, y.
Yes, yes. Everything is symmetric here with respect to x and y. And it's not directional. Then I will need also this concept of partial mutual information between x and y, given another vector or random variable z. And this is defined like this. Again, it's the Kullback-Leibler, expected Kullback-Leibler divergence between the joint conditional on z and the product of the marginal, both conditional on z. Okay, now I will apply this to stationary random processes. So I will need some concept. This is just a review of basic things about stationary random processes. So I will denote by gamma k the autocovariance at lab k, as usual. Capital gamma k will be the autocovariance matrix of a collection of k consecutive random variables. Rho k will be the autocorrelation function at lab k. And I will need especially the notion of a partial autocorrelation. The partial autocorrelation can be seen like that. Suppose that you consider the optimal linear predictor of the value at time t using k past values. And, you know, it turns out that because of stationarity, this coefficient here is a number between 0 and 1, between -1 and 1. It's a correlation. And it measures the association between xt and xt minus k once you have sort of accounted for the effects of the intermediate random variables. So the partial autocorrelation function is a key thing that I will need, a key concept that I will need here. Now, for Gaussian processes, this the world is very nice and easy. So phi kk is a conditional correlation. And the mutual information between xt and xt plus k, so the current value and the future with a lead time of k, is just a function of the autocorrelation at lag k. So it's this transformation of the autocorrelation at lag k. And the mutual information index is the square of the autocorrelation coefficient. Now, if you condition on the intermediate random variables, then you have the partial mutual information. In the Gaussian case, it's a function of the partial autocorrelation at lag k alone. It's this transformation of the partial autocorrelation, or if you take the mutual information index, it's the square of the partial autocorrelation. And these things, as we know, are efficiently computed by the Terpin-Levinson algorithm. Okay, now a first result is the following. I stated as a theorem, I should write it as an observation. Because the story is the following, you know, in a Gaussian environment, multivariate dependence is a function of the pairwise dependence, essentially, of the covariances and correlations. Can we have something similar when we want to express the dependence of the past and the future? Can we express the mutual information as a function of the pairwise dependencies between the random variables? Yes, once you condition on the intermediate random variables, and that's the observation, the main observation. So let's start by defining by pi k the partial mutual information between xt and xt plus k, conditional on the intermediate random variables. So this is a partial mutual information between these two guys. Then you can write the mutual information between the past and the future as a cumulative sum of all these partial dependence measures. So the past for me will be this collection of random variables from time 1 to time n. The future will be from time n plus 1 to n plus m. Then you can show that the mutual information is the sum of all these things, of all these partial mutual informations. And that's, you know, it's a sort of an extension of the classical result that you have for Gaussian random variables, in a sense that a multivariate dependence measure is a function of the pairwise measures. Now, you could say, well, let's look at these things. So here I should try to measure these things and estimate these things. Actually, these things are not very easy to estimate because, you know, pi k is nothing more than the expected log copula between the two variables conditional on everything else. And so you have an object that is multidimensional, and to estimate this object, there are, you know, several proposals in the literature using k-nearest neighbor or non-parametric methods, but still you face the curse of dimensionality because these objects involve k random variables, so they're not easy. I will take another route, as you will see. Just as an extension, I consider the indefinite past. The indefinite past starts from the time of the dinosaurs up to now, and the indefinite future would be starting from time n plus h to infinity, right? So let us consider now the indefinite past and indefinite future with a lead time of h. When h is equal to 1, then there would be just the future, etc. Now, the mutual information between past and future, looking at the previous result, would be just this cumulative sum. And of course, if this quantity converges, then you say that the process is absolutely regular, right? If this quantity goes to 0, as h, the lead time goes to infinity, then this is called information regular. But we will be concerned with processes such that this converges, in a sense. So the process will be absolutely regular. Okay, so now
this is funny to call this absolutely irregular because Ibrahimov
yes.
and Rosanov also introduced notions of mixing, which is called absolute regularity. And I don't know, I don't really directly see the relationship.
Yes, you're right. There is some, you know, this absolute regularity comes from a paper from Jewell and Bloomfield. Yes, that's the definition they have. But there is some indeterminacy on this, the use of absolute regularity. So Ibrahimov and they use another. Yes.
Maybe I'm not sure I should.
Okay, so this specializes in the Gaussian case very nicely because the partial dependence measure are a function of the partial autocorrelation. So this is the result for Gaussian processes, and this is the formula that is well known. So the mutual information is this cumulative sum of the partial dependence measure that we saw before. They depend on the partial autocorrelation. Just as an example, very simple Gaussian AR1 process, then the mutual information between past and future depends only on the square of the autoregressive coefficients. The partial information, so the index of mutual information is just the square of it. The same holds for the log normal stochastic volatility model. This is a model that is used in finance, so that the underlying process YT would be the log volatility. So if the log volatility is an AR1 process, then XT is formed like this. Again, the mutual information index between past and future is just the square of the phi coefficient. The previous absolute regularity condition does not include processes which have mutual information that is in diverges. For instance, long memory processes or non-invertible processes, for which this mutual information is not diverges to infinity. Also, you know, for classes of very simple processes, like an Arch1 process, you know, given that these processes are formulated in terms of the conditional density, it's not so easy to, so the mutual information is not available in class. This is just an approximation. Okay, so let's come to the contribution, say. My point is the following. I'm considering a set of measurable transformation of XT. They will represent a set of functions with the same characteristics, so that they are members of a basis, a set of basis functions. So let's call these functions H1t, H2t, HRT. Suppose that there are such functions. I'm assuming that these functions are non-singular, which is this condition here. So they sort of carry information that is non-singular. We collect these functions of xt into a vector H, capital H, sorry, bold HT. This is an L by 1 vector. And I will denote the cross-covariance matrix at like 0 by gamma H0, and the cross-covariance function by gamma HK. Okay, I will say in a while what kind of functions I'm considering here, but once these are available, they can be combined linearly into a new process, ZT star. And the linear combination is such that the coefficients are normalized in this way, right? So that's a weighted linear combination of these functions so that the betas are normalized in this way, in this generalized way. Then I may consider, this is optional, but I may consider a transformation of this linear combination. And typically this could be either the identity transformation, so leave the things as they are, or you can use a normalizing transformation. So I could use the quantile function of the standard normal to sort of normalize this variable. So the G could be this kind of thing. So you take the probability integral transform of ZT star, and then you use the quantile function of the standard normal distribution. Okay. So now, then I define the most predictable aspect of XT, which is this transformation G of beta transpose HT, which satisfies a constraint and maximizes the mutual information between the past and the future of Z.
Is this transformation one-to-one?
No, not necessarily. As we will see, it's not one-to-one. In typical examples, it's not one-to-one, but yeah, it could be or not. And the second most predictable aspect can be also defined, you see, as an orthogonal aspect, orthogonal to ZT in this sense. So think of another transformation, G of psi prime or zeta prime HT, zeta prime be another vector, which is normalized in the same way. but it's orthogonal to beta in this sense, in the metric of gamma H0. And the second most predictable aspect would maximize the mutual information between the past and the future of WT under these constraints. Right. So this is all very nice, but it's typically difficult to get because measuring the partial mutual information of the ZT process is typically difficult. So I will scale down my objectives and do something easier. So I will use this definition. The most predictable aspect of XT is this same transformation as before, but what the maximum now is, say, the linear mutual information measure. So as if the ZT were Gaussian, right? So essentially, everything boils down to computing the autocorrelation, the partial autocorrelations of this process. So things will be much easier. So this guy here will be the partial autocorrelation function of ZT. And you can also define the second best predictable aspect subject to the same orthogonality conditions, but now you maximize the mutual information measure for that. Okay.
Sorry,
yes.
What is the relation between the most and the second? You know, there seems to be like, you know, the criteria. I mean, when you say first and second, it gives you like an idea of order, no? Like
yes, there is an ordering. So the first one should capture most of the dependence. The second linear combination should be orthogonal to the first according to this. So you see there is an orthogonality relationship between.
Okay, I was missing that part. Okay.
And it's like a sort of principal component kind of thing.
Okay.
Right. So there is an ordering that goes like this. So the second best linear combination is you combine the same function, right? You have decided upon a set of functions, features of the process that you would like to investigate. You combine them linearly, but with a different loadings. And these loadings are normalized so that.
Oh, right, thank you. That was
what did I do?
Probably because you touched. Probably because you touched.
Because I touched.
Yeah.
So I need your special touch now, Paul, to bring it down to.
You give it twice.
No,
twice.
No,
Okay. Now it's right. So you see, this is.
Okay, yeah, I see the beta from the first.
Yes, the beta is the first.
In
right.
the first, no, but okay, you got to go the beta coefficient, then you make the orthogonal to the other. Okay.
Yes.
Okay. I missed that part. Good.
And how do you choose R?
Yes, I'll go back to that. For me, it will be fixed,
Okay.
but I will discuss it in a moment. That's. So we start with the basis function. So what kind of basis function? Well, you know, HT, you could think of yourself as relatively free. This is a feature vector. You could look at a feature that you would like to measure. But you see, what I will, my preference goes for two sets of basis functions. One is the hinge set of hinge basis functions, and the other one is a set of logistic basis functions. So this basis function have this characteristic. They are evaluated at location shift of XT. So they apply to XT minus a quantile of XT. This denotes the alpha j quantile of the marginal distribution of XT. And one set of relevant basis function is the hinge basis function, which are described like this. So you see, these are the location shift. I should have an alpha j here in parentheses. I take the short notation for it. And so suppose that you have only two basis functions located at the median, for instance. Located at the median, this would be the first function of XT, and this would be the second, right? So that's a pair of hinge basis function. Now think of, if R is larger, think of locating them at the quartiles of the distribution, deciles of the distribution, like this, right? So this is one basis. And the other one would be a set of logistic functions, again, located at location shifts of LT, like here, right? So this is, again, the quantile. And just to have a look at them, they will look like this. So these are, for instance, are 4 members of this set located at the quintiles of the distributions. Of course, you could have something else like natural cubic splines, Fourier basis, or whatever, but they seem to work less well. And of course, the choice of R is important. You need a decision about how many elements of this basis. You could think that R could be allowed to vary with the number of observations also. And you could do, you know, then the theory would be much more difficult, the theory of inference. At least for me, there is some contribution by Chen and Shen, for instance, that they look at a method of sieve extremum estimation. But I will keep R fixed, and later I will say how we can select it. Okay, so inference. Inference deals with estimating the quantiles, of course. The quantiles can be concentrated out of the problem because they are the quantiles of the distribution. So you decide R. Then you have to estimate some quantiles of the distribution, and then you have to estimate the betas. You estimate the quantiles with the sample quantiles. Then you construct the vector HT. You construct the covariance matrix, and then you need to solve this problem. You have to maximize this criterion function with respect to beta. So what is there? You see, this summation should be infinite. Here I truncate, so I have a non-parametric estimator of, here I use a window of the lags, acting on the lags, so that I leave out high border partial autocorrelations. And Alt would be the bandwidth parameter or the banding parameter of a kernel. So essentially it works like this. This guy here are estimated from my sample time series. So I could estimate the partial autocorrelations of my Z by a method of moment estimator. And then I construct this regularized partial autocorrelation so that you see this is multiplied by a weight. Now I use this kernel here so that the weight is equal to 1 for the first LT partial autocorrelations, and then they decline to 0 linearly according to this trapezoidal kernel. So I'm using actually 2 times LT partial autocorrelations. And of course, I need to decide this parameter. So this is the bandwidth parameter is chosen at a value so that so in a previous paper, we applied a rule like this. This is like a joint test on a number of partial autocorrelation from LT to LT plus capital K, say. And if they are jointly zero, if you don't reject the null that they are jointly zero, then you select the banding parameter. So we have a criterion for choosing that, and we have a criterion also for selecting R, which is based on the mutual information criterion proposed by Li and Xie. So it's like penalizing for the complexity induced by a choice of R. And we sort of customize to a problem the criterion. Typically, the maximization is carried out using a numerical optimization routine in MATLAB, for instance, and the initial value of beta hat for the estimator of beta can be taken from an eigenvector of this matrix. It's very efficient to use one eigenvector. So of that, you look for the eigenvector so that the mutual information is a maximum, and then you start from there. Optimization is usually very fast. Okay, so does this work in practice? What are the properties by which we estimate these things? Well, there are some regularity conditions concerning the process itself, XT. First of all, you need to guarantee that the quantiles are sort of unique. So you have restrictions on the marginal density function, which has to be continuous. Then you need conditions also on the mixing properties of XT as well. You need a moment condition here, which you can avoid. So this condition is not needed if you use a set of basis function which is bounded, like just the logistic basis. The logistic basis prevents, you don't need the existence of moments for that. You need the summability, and you see the strong mixing property with these sides can be replaced by just the summability of the alpha coefficient. So you get a simplification of. Then you need conditions on the set of basis function that you choose. So you need conditions on the Lipschitz continuity, which is guaranteed for the kind of basis that we have considered. You need some rule about the bandwidth parameter by which you sort of truncate the partial autocorrelation pattern. And finally, you have an identification condition, the existence of beta, the true beta, right, for your problem. And you see, that's not very easy to be very specific about because what if you work out the first order condition for a solution, then you come out with a nonlinear system of equation, and so we assume the existence of a fixed point solution for this set of nonlinear equations. Okay, under these conditions, you know, you have a consistent estimator of beta, and then you have also some result on the asymptotic normality of the beta hats. Okay, coming to applications. How much time do I have, Paul?
I think so
15
around
minutes?
15. Oh, in fact, we don't have.
We have no application.
You were delayed, and so
No,
maybe
sorry.
half an hour if you want.
I will.
It really depends on you.
So now some illustrations. The first one is the following. Suppose that we have a log normal first order autoregressive process formulated like this. So the logarithm of xt is an autoregressive process, Gaussian autoregression process. Now the coefficient is 0.5, so we know the mutual information for this problem is 0.1438. So we know the true value. So how can we reconstruct this? I do this by simulated Monte Carlo experiment. I sample 1,000 series from this process with sample size 100, 250, and so on and so forth. And then I work out my most predictable aspect by considering a set of basis function. I select the hinge basis and see what happens. So this is a simulated series, right? So this is a log normal autoregressive process, and that's its sample ACF, right? Remember that the coefficient here is 0.5, the autoregressive coefficient, and this is the process XT. It's a sequence generated from that process. Now I work out the transformation, the optimal transformation, and I get this series, right? And if I plot ZT versus XT, the transformation is very similar to a logarithmic transformation, right? So this is what you would expect, right, in this problem. And this is the sample ACF of the transform series. As you see now, things are pretty much more in line with what you expect, this coefficient being 0.5, the first autocorrelation. And if you now replicate this 1,000 times for sample size 100, blah, 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 you get closer and closer to the trillion through mutual information, which was 1.14 something, right? Which lies here, and you get closer and closer to that. So in this case, you had a monotonic transformation. Another example is this process, which is often used in this literature about nonlinear dependence. So Phokianos, Pistillo, and Zhu, they use this for an illustration. So this is a nonlinear moving average of order 2. Is the product of epsilon t minus 1, epsilon t minus 2, where epsilon t is IID normal, standard normal. This process is serially uncorrelated, but not independent. In fact, the transformation of the process have a moving average feature of order 2, for instance, the squares. Okay, I generate a sample realization of 1,000, and it is plotted here, right? So this is 1,000 observations from this process. Then I consider 2 hinge basis functions located at the median, Zhang, like that. And this is the optimal transformation of my ZT star. You see it here in parentheses, is the weighted combination with the betas, with these 2 betas of the 2 hinge basis function, and then I play out a normalizing transform. And this is what it is, this is the transform time series. Now, if we look at the autocorrelation pattern of this time series, we do recover serial dependence of order 2. So in red, you see the red points are, in this parallelogram, are the autocorrelations of the original series, whereas in blue, you have the autocorrelations of this transformed series. So you recover that this is as an MA2 structure, in a sense. And if you plot the transformation of ZT versus XT, that's the kind of transformation that you have. And this is not one-to-one. The transformation zooms out the zeros. As you see, there are many zeros, or concentration of values around 0. So these are stretched, and you see the big values are shrunk, are sort of reduced in size. Now, this other example, this with the US index of industrial production, what happens there? This is a quite regular time series, with some autocorrelation pattern, but it's disturbed by this the effects of COVID-19, right? So you see that there is a big increase in the amplitude of the fluctuation. This is because of the lockdown, and this is the subsequent recovery. So this is the growth rate, the monthly growth rate of the US industrial production. So monthly growth goes down during the lockdown, and then after the recovery, it goes up by a large amount because the previous month was way down. So what happens here? Of course, here stationarity is not cannot be maintained, but you see, I construct my most predictable aspect of this time series. And here I use, because of these outliers and this structural change, I use the logistic basis. Now, what happens here is that the transformation that I estimate is actually sort of a logistic. So it's a robust transformation of the time series so that these values are, reduced. And this is the transformed time series. As you may see, something has been going on, not perfect, but, this has been put back into normality, and now this is what you find there. In this case, there is also a second most predictable aspect, which is relevant, and it is the volatility of the time series. So the most predictable aspect, the second, because of this combination here, this was sort of a level, a robustified level. right? Because of the logistic function that I'm using. This is a contrast, so it's more of volatility. Exactly, volatility.
So you can make money with this.
Maybe with the next plots, because
Oh,
the next one is with
because
financial.
I once had a company predicting the size of the VIX, which way it was going to go, and it was working very well on paper. But once we got into the
Yes.
water,
And then it didn't work anymore.
well, there was a cycle, and one of them was down, and the investor decided to bail out. But it helps to make money.
So last example is the S&P 500. S&P 500 is this time series. These are daily returns. Daily returns. They are serially almost uncorrelated, although there is something at lag one, a negative autocorrelation at lag one. And again, this is a sort of a test bed, because we know we also teach the students, so look, the series is uncorrelated, but it's not serially independent, because, you know, volatility is a big thing here. And in fact, you see that the most predictable aspect of this time series is volatility itself. This series is highly correlated with the absolute values of the squares of the original time series. So volatility is indeed very predictable. Now here I use two basis functions located at the median. The bending parameter is 10. This is the autocovariance matrix. So it's a very simple estimator of the most predictable aspects, so that I can visualize the solution. So this is the set of the betas. So the betas have to satisfy a normalization constraint with respect to this metric, the metric of this matrix. So they have to lie along these ellipses here. And this is the value of the objective function. As you may see, the value of the beta is identified up to a sign change, right? You can switch the sign and still the solution will be the same. This is the same indeterminacy that you have for principal components. So that's my solution. You could reverse the sign of this series, nothing changes, and this is the meaning. And the normalizing transformation will be this. The normalizing transformation will be this. Yeah, that's the plot of the ZT star, the linear combination of the two basis functions, and this is the plot of ZT versus XT. That's the transformation that I'm using. Finally, the last point is that, okay, now I have my most predictable aspect of time series. Can I have a test for independence built on that? Or a test or unpredictability built on that? Well, you see, the idea is to apply, what happens if I now consider ZT as an observed time series, and I apply a test of serial dependence, like the classical ones that we have in the literature, for instance, Hong's Portmanteau serial correlation test, where you see these are the autocorrelations there is a square that should not be there. The square is not be there, so that's a typo. These are the autocorrelation of ZT, and this is a kernel. The square is there. Now that's okay. The square should be there. This is a kernel KJ, and so on and so forth. Now I will sort of stop here. You know, I conduct this test. So it turns out that this test is quite effective. It is slightly oversized because, you know, in a sense, you are sort of overfitting features sometimes. So you need to be careful when you choose R too large. You need to be careful because R too large means that you are over rejecting the null of say serial independence or but you see, it seems to work well, and I tried out under the null several nulls. For instance, this is my preferred test, and the size properties are okay for R equal to 1. So this is the size with 100 to 5,000 observations. And I also, then these are other, I also look at the power of the test versus, you know, classical nonlinear processes in the literature. And well, the power properties are pretty good, except perhaps, you know, less so for the Garch. Let me see if I have it here. So processes that have a substantial MA1 feature, like say Garch, such that the squares are an ARMA process, then you see sometimes, you know, the power is less good. But, you know, it seems that things can be made to work. So one idea I would like to conclude with is the following. The transformation is not one-to-one, but can I predict features of my process? So let's go back to the standard and poor example. So suppose that I came up with the most predictable aspect of this time series, which is this, right? I could fit an ARMA model. For this is a nice and linear, amenable to a Riemann model fitting by some classical model, and then I could predict, you know, some density forecast for the future. Then it would be nice to invert it and to go back to the. So suppose that I have a range of predictions in this area. Sorry, and then I would have to invert it to understand features like measures of risk and so on and so forth. This could be an interesting thing to do. I haven't done it yet. I only found the paper that from another perspective, it has populi of xt and the absolute value of xt for a financial time series. Is this paper by McNeil on the V transform, which has a similar idea of inverting this V transform in this case to a sort of get measure of value at risk or risk measure for expected shortfall for the process. So I think I'm done, Paul. Thank you very much.
Thank you. Are the comments?
Yeah, I was wondering, I mean, so the goal is to get the most predictable aspect, you know, with respect to a family of basis functions. So my first question is like, the aspects of the series, you fix them beforehand? I mean, because you say, well, I'm going to try, I mean, I got a return time series, and so my aspects will be the square of the returns to as a proxy of volatility or something else. But I mean, so you just, I mean, so the aspects are the ones that you target for.
Yeah, I see what you mean. It's not, you know, the functions that you use are flexible enough because you see, after all, you are combining functions like this or whatever.
Oh, so that's something that was so related to my second question. Also, the basis functions are the ones that builds up your aspects.
Yes, yes. Okay. So these are the H. Okay. My H functions are this.
Yeah. Okay.
So yeah, for instance, if you have opposite coefficients, then you have a one-to-one transformation.
Okay.
If you have same sign coefficients, then you have volatility kind of.
Okay.
So you see, also here, you see, you could have attach some coefficients that may tell you whether you have to.
Okay.
What kind of aspects they.
Okay.
So are the betas that determine the sign attached to the to these functions.
Okay. Okay. So you're looking to optimize among all the transformations that you could, and these are.
So the outcome is not known a priori. Of course, you know what you're looking for sometimes.
But so you choose your basis functions in order to like get to maybe.
You know, the choice of the basis. Yes,
like
I would choose this step for problems where I'm not sure about the existence of moments. Right.
Okay.
This is, for instance, you know, you could use also the natural cubic spline, but you know, you have to deal with powers of so polynomials, and maybe you don't have this moment conditions that are fulfilled for financial time series if the variance does not exist, for instance.
Okay.
I'm sorry, I have a question from someone online. I is asking, can you explain why you choose the logistic function in slide 18?
Slide 18, this one.
That's yeah.
Yes. Why? Well, you see, because essentially this is a transformation that can robustify. So suppose that you use a few quantiles like these deciles, and there is no transformation. Your series is actually the most predictable aspect, right, of cell. Then you see such that you preserve this monotonicity and linearity, and you get back to the original time series. So instead, if you need to robustify and cut the extreme of the time series, this is very useful. So this is useful in all situations where you want to robustify your inference, in a sense, because all the H's are bounded. So that's why it's useful.
Because the other function you use is the one which is used usually by,
Yes,
that's the maximum, this one, H.
This one, yes.
It's the so-called ReLU function.
The hinge, or I don't know, yes.
It's very much used in the deep learning
It's
context.
sometimes, yes, use the Mars algorithm, for instance.
Because when you use a deep neural network,
Yes.
and you iterate those things, you obtain still things the same way, which is something exceptional for those deep networks.
Yes.
I didn't understand your bandwidth condition, your result, because it seems that it's similar to a kind of semi-parametric estimation. So
yes.
Typically in semi-parametric, you have so to get the root T convergence rate for your
yes.
estimate, you have to kill the bias and to kill the variance, and then you obtain a range of bandwidth. And
yes.
here you don't have exactly a range of bandwidth. You simply have you can choose the bandwidth as small as possible, so which is
so the idea is that here you're accumulating things, right?
Okay.
So any error here is multiplied, so it's doubly cumulated, and so this is why the rate on the DLT, which is this one, right? Is the fourth root of T, of capital T. So you need to have a kernel that goes down quite rapidly, so that the estimator is consistent. So that's the condition for that, yes. So I need this rate. The further condition is that you need at least as many autocorrelations as the R, right, that you use. But this is because, errors accumulate, and to make estimation error go to 0, then this is what you need. Yes. Then in practice, I apply this rule, which is consistent with that, in a sense that, you look at the smallest value of LT, so that the next capital K, which I choose 5 usually, depending on the frequency of the data, but so that they are jointly 0. So then you just, so it's like a multiple test, right? But yeah, that's what we do.
So you don't need a parametric model to run because you start from the sample correlation, no?
Yes.
And so you should expect that there is a long dependence in the data, the index should be infinite.
Yeah, long dependence, unfortunately, is ruled out.
Okay.
Because the true function does not converge.
Okay. Yeah.
So this is everything is for short math.
Thanks.
Okay.
No more questions. So thank you again.
Thank you very much. Thank you.
So I think now it will be that should be the talk by that's your talk now. Okay, I will put it on the computer top. Did I get it?
Victor, I'll read your mail.
Martin, yes, sorry. So there are two
Yes.
Yeah, so
files.
when I finish one,
Go with the second. Okay. Okay, no
how
problem.
do I work it out?
Okay, I will I just suspended the record and we come back to this very fast. So you begin with the old and new results.
Excuse me?
You begin with old and new results
Yes, so I wanted to put some context.
before.
Yes, I have some context, but
That means
I'll
the
try
other
to
guy
go.
maybe? Or- sorry, do you want to open the first?
Yeah, the
other
first presentation,
The other one,
the one with all new results.
growth of orders, this one?
You see,
You want this one?
not that one, that's the new result.
Okay, this one, okay.
Yeah, that one. Okay,
So let's do it. So. Okay, so here, that's very easy this time, I'm sorry. Sorry for the others, because okay. So, so Victor, that's a pleasure again to see you, that you came finally to Paris.
so when Paul asked me if I could give a talk, I was very hesitant because I haven't done very much new lately. But fortunately, there are other people that have used my work, and I was able to do something was a little bit ahead of them. So the story behind the new results is Yuval Perez. I gave a conference on inequality. The inequality is as follows: you have the non-negative variables, no assumptions, just non-negative. A function which is concave with p of x0 equal to 0. So imagine that you have non-negative variables, no dependence assumption. You want to estimate the expected value of that. So what happened was, this is work that I did 30 years ago, that the expected value of that function is less than or equal than a constant, a universal constant, than the expected value of the same function of a sum of independent variables with the same margins. Okay, so this inequality remained buried for many years until Yuval Perez. I gave a talk about this, and I said at the conference, I said, this ought to have some applications. I was looking for that. And when Yuval Perez went to work at Microsoft, one of his Mac Ariashow, who was working there, came and asked him a question about how to deal with servers, which were dependent. How do you deal with that? They are not independent, so it's not easy to deal with how you transfer the information. And he said, well, look at Victor's book. And in there was something about this. And as a result, he published a paper with someone from Yahoo, in which they found the best constants, and they found the optimal algorithm, epsilon optimal. And so I was able to use their results to come up with something simple, but I think that you will find it interesting, I hope. So this is the context of this talk. Okay, another inequality that came up out of this was an inequality for maximums, arbitrary variables. The probability that the maximum is bigger than p is less than or equal than the same constant as before, the chart constant, and the probability of the maximum of independent variables with the same margins. That's just an observation, but I have an application of that. So anyway, so let's continue. I will introduce you to, I have two decoupling approaches. One is the decoupling approach that basically decoupling, the idea is to replace dependent variables by independent and through inequalities or limit theorems like our friend Adam Jakubowski has done. So there are two types of decoupling that I am aware of. One of them is the decoupling that was initially developed by Burkholder when he was trying to extend the martingale theory to Banach spaces. And what he found was, with his student McConnell, an approach through decoupling to handle the problems involving Banach spaces. So that was in 1983. Now, I was a PhD student around the time, and I came up with a decoupling inequality as well, having seen what was being done on that, and I showed it to my advisor. And he said, this is not optimal. He threw it on the trash. That was for quadratic forms. So I got very sad. Fortunately, a year afterwards, when I was getting ready to come to the POLEDI conference, I came up with a result for martingales, and I will show you that result as well. And the result is similar to the previous one. You have a martingale different sequence, and you want to calculate the LP norm between 1 and 2 of the martingale difference of the sum. And it just happens that by using Burkholder's results and some tricks, extra tricks of my advisor, you were able to show that that LP norm is less than or equal than the LP norm of a sum of completely independent variables with the same marginals as the martingale difference sequences. And the challenge for you is to find the best constants and to find an application. So anyways, that's the context. So I'm going to teach you a little bit of decoupling. I will go fast over this because I already gave you
Who was your advisor?
Michael Glass at Berkeley. So anyways, I'll tell you what I used from his work to develop the inequality in addition to Burkholder Gandhi. So anyways,
Sorry.
how much time has gone? I hope a lot.
That's up to you a bit, you know.
Where is the time?
The time is not on the screen, but it's
Oh, okay. Well, anyways,
3:26.
so the theory of martingale equality. So I already spoke about this, and the beginning of the what I call tangent decoupling is a paper by Burkholder and McConnell, which appeared in Burkholder 1983, and he extended the theory of martingales to Banach spaces. Now, here is the consequence, or here's the background behind decoupling, in case you haven't understood that. Okay, so there's a little bit of measure theory that needs to be understood so that you can get the sense. I will give you some inequalities about this. So suppose that you have two sequences of random variables adapted to the same sigma fields f sub I. Then the sequence d sub I and e sub I are said to be tangent with respect to f sub I if for all I, the conditional law of d sub I given f sub I minus 1 is equal to the conditional law of e sub I given f sub I minus 1. Where L of d sub I given f minus 1 is the conditional probability law of d sub I given f sub I minus 1. So these are variables with the same conditional distributions, but that's the only assumption. Now, we want to find from here a sequence that is conditionally independent and has the same properties. And so I'm going to show you how to construct it. Actually, it would be easier if I use the blackboard for that. Can everybody see the blackboard?
Yes, yes.
Or maybe not, because this is maybe not as easy to show. If I show you in the blackboard, it will be easier to. So it's appear in the paper Annals of the Institut Henri Poincaré. So I'm happy to do that. So the idea is this. So I have D sub I, D1, D2, Dn, arbitrary variables. And I want to construct a sequence E1, E2, up to En that is conditionally independent such that these two are tangent with respect to a sigma field. Okay, now the way what happens is that the E sub i's are going to be conditionally independent given the sigma field of the D sub I. Okay, so now the question is, how do I construct it? Before this construction, the statement was very abstract, at least to me. I couldn't really understand it, but this is the way I understood it. So the idea is you first take two independent copies of the same random mechanism. So these two are independent. Then what you're going to do is conditioning on D1, you take two conditionally independent copies of the same random mechanism. Okay, so these two are conditionally independent given F1. And you do the same for the next one. D2 takes you to E3 and also to D3. So again, D3 and E3 are tangent with the same conditional distributions. Okay. Now, in order to be tangent, they have to have the same conditional distribution given the past. So if I close this, I have F sub I is the sigma field of D sub I, or and then F sub I prime is the sigma field or of the D's and the E's. So they are adapted to the same sigma field. Okay? So they are tangent. Now, one thing that one can observe is that by doing this sequence of variables is conditionally independent given this sequence, because the dependence between them only depends on the past D's, and otherwise they are independent. So it's only if you know that these variables are independent. Do you agree? Is there any question? So that takes care of a lot of mathematics. So this shows you how to construct. This is not the only way to get a tangent sequence or decoupled sequence when you with these properties, but you know, there was a breakthrough paper which was related to work of Adam Jakubowski and Chłapin and Wojcinski, where they showed that for any sequence, you can always construct a decoupled sequence. So there's more than one way. Okay, but this is just one way that I understood what was happening. Anyways, in this, so these are the D sub i's, these are arbitrarily dependent, and these are the E sub i's, which are conditionally independent. So I'm going to show you that linearity of expectation is the first decoupling equality. Okay, so I'm going to show you that here. So linearity of everything goes back to linearity of expectation as far as decoupling is concerned. So we have expected value of D sub I by linearity expectation is this, which is equal to the expected value of D sub I given F sub I minus 1 prime, the one that includes the D's and the E's. Okay, if there's a question, please stop me. And then, since they are tangent, they have the same conditional distribution, so I can replace this by this. Okay. Now, since the E sub i's are independent given the G's, okay, given the D's, I can replace this by the expected value of the E sub i's given the sigma field of the D's. So this is the sigma field of the D's. Because they are independent, I can drop the sigma field of the D's. Now then, since this is a sigma field, I can take this expectation out by linearity of expectations, and then I can take this expectation out again, and that gives me what I was looking for by iterated expectations. Okay, so decoupling of tangent sequences is reduces the first decoupling equality was basically linearity of expectations. Okay, and then the task of people was to find other conditions and other functions for which there were relationships between the two. And the first one to obtain a result in this general context was Zinn. Joe Zinn in Texas A&M, he found a way of comparing tangent sequences in certain powers. Then Kwapin and Wyszyński got into the game, and they developed tail probability inequalities and various things. And LP norms. And Hitchenko, he found the best constant on the LP norm of you have arbitrarily dependent variables. You find the LP norm of that. There's a constant. The order of the constant is the best times the LP norm of conditional independent variables. Okay, so that was Hitchenko's, and that was used to prove the best constants in Rosenthal's inequality. So that's sort of the history behind this type of decoupling. Can we go down? Okay, now I have written 2 books. One is on decoupling, one is on self-normalization. And as it happens, I came to decoupling, to self-normalization through decoupling. I was in Illinois, Urbana-Champaign, and I asked, what's a good question in probability? And Duke told me there are a lot of results in harmonic analysis where you take the ratio of a harmonic function over super harmonic function, but almost nothing in probability. There was something of Yor and Jaka, but there was very minimal work. So anyway, so I kept that in the back of my mind, and I developed a self-normalized inequality. So let's go up. That appeared, okay, so let's go up. So in the Annals of the Institute Henry Poincaré, I developed this self-normalized inequality, except that G was equal to 1. G is important, I'll show you why. G is...
You have to touch again.
Oh.
You did it very big.
Twice.
2 times.
No,
Again.
so it gets smaller. It goes through a cycle, so you do
One more
twice,
time.
do it again twice.
I cannot do it.
Again.
Go on.
I don't know.
Well, anyways, you can see here.
Yes.
So basically, this is the moment engineering function. So this is the expected value of e to the lambda, sum of the arbitrary dependent variables, is bounded by the square root of the expected value, forget about the g square, of the moment engineering function, twice the moment engineering function of the conditional independent variables. So basically, what this gives you, using this, it extends exponential inequalities for sums of independent variables to martingales. Because here, if you condition on the sigma field of these, you have a sum of independent variables, so it becomes like playing a game. Now, the G, so this works for any G which is measurable with respect to the D's. So you can put a constraint. So you can put a constraint, and then, so let's continue, and that
I
led
cannot
to.
do anything, you have to touch the screen.
No, but it's like,
You blocked it.
go up, go up.
Ah,
Hein?
This is trying to stop.
vas-y, je sais pas le faire.
Like, give it twice again.
It's
Can you
cycled.
do it?
It's cycled.
Huh?
It is cycled. Tommaso did it before.
Yes.
Okay, well, you know, I'm nervous, so I am nervous, but, okay, so let's go to Berns. So this is the decoupling inequality. The momentary function of the sum of arbitrary variables is bounded from above by the square root of the square of G. You know, here is G, there is G square times the square root of that. This is basically reverse Holder's inequality. So that's the way this is true. Everything, all the proofs that I have are very easy. So because if you want to get general results, it's hard to use difficult techniques, at least in my opinion. Anyway, so I'm going to introduce Bernstein's inequality. So I assume that the x sub i's are independent, mean 0, and then let's go up. Okay. So let's bring it up. So this is Bernstein's inequality, sum of independent mean 0 variables under some conditions. This is the variance. And then in 1999, I used what I did in in Henry Poincaré, in a paper in the Annals of Probability. I introduced this type of inequality. So the probability of the sum of the martingale difference sequence over its conditional variance bigger than x is bigger than the expected value of e to the minus x squared conditional variance over this, given that the sum of the pi's over the conditional variance is bigger than x. So this is the beginning of something with martingale over a super martingale or sub-martingale, okay? And most of the inequalities that depend on the moment generating function technique can be proved this. You can find that in my paper. Now, this is also less than or equal than this. So if you know the distribution of Bn squared, you can get this bound. Like if Bn squared is chi-square or something.
Sorry,
I didn't get close.
I didn't, sorry. I was too fast.
Okay, so now if I let G, the G that I had put there, to be the indicator that 1 over the conditional variance is less than y, okay, it transfers to the upper bound, and then you get this inequality. So it's the conditional you have the martingale or the conditional variance bigger than x, 1 over the conditional variance less than y, and you get from that you get you know, an exponential inequality which reduces to the Bernstein's inequality if the conditional variance is a constant. So it's a sharp extension. Now, so let's go to the next slide. Okay, I'm going to skip this one because I promised that we were going to leave early. Okay, because basically it's the same as what I was presenting. Now, okay, so let's skip this. Now, one thing that you should know, or I don't know if you know, is Hopkins inequality. Hopkins inequality tells you that if you have a convex function and you take an expectation of the sum of sampling without replacement, that is bounded by the expectation of a function, convex function of a sum of independent variables. Okay, you can also decouple that. So it's a different inequality, but the upper bound is conditional independent, not for all convex functions. But the inequalities that I would show you extend Hopkins inequality that you obtain the reverse of Holder's inequality. Okay, so again, linearity. So now I'm going to talk about complete decoupling. That is to say, you are going to replace the variables by completely independent variables. Okay, so again, everything is related to linearity of expectations. This is easy to see, so I'm not going to spend that much time. Just to say that how to construct the independent variables that become the upper bound, or the ones that appear on the right-hand side there. You repeat the process that this gives you the these. They are arbitrarily dependent. Repeat it n times. And then you take the diagonal variables. The diagonal variables, d sub I super I, have the same distribution as di, but they are independent. Okay, is that clear? So that's how you construct them. Now, okay, so now if you do something without replacement, okay, so we are going to show how to do complete decoupling of simple random sampling without replacement. So we have again, sampling without replacement. Everybody knows what it is. So let's go up. You have okay. You have the DIs are the sampling without replacement, and then the YIs are the sample with replacement. And so you have dependent variables compared to a sum of independent variables. So that's the message here. And this is the inequality that Hopfield proved. And so there's also an inequality of this type, exactly that, by Shao extending things to negatively associated variables. So this was done, in 2000. Now, so if we take, so let's go up. So I want a lower bound for Hopkins inequality. So that will come from the result of Makariachev and Spiridenko that was developed. It was developed in order to get algorithms for distribution of loads in parallel machines. More precisely, to develop stochastic optimization tools for energy efficient routing, load balancing in parallel machines. You can read the paper. I have a reference. It's 2018. Now, you see, is the good thing about Google is that I get who cites me. So that's how I found this paper. Okay, so now let's go up. Okay, let me just read this. So the context of the result is you have pi, which is a Poisson variable with mean 1. And pi is going to be independent of the d's and the y's. Now I'm taking y's are completely independent. The d's are the arbitrarily dependent. Okay, so I'm completely decoupling. So I have pi is a Poisson variable with mean 1. Okay, and d sub i's are dependent. Y sub I is like I independent. That's why I chose that. Then the inequality is this. If you take a sum of, you take a convex function, phi, okay, then for any convex function, the expected value of phi of the sum of yi's is less than or equal than the expected value of the function of pi times the sum of the i's. In my paper, under the supervision of Michael Glass, I proved this for special functions, but I didn't have the sharp constants. And then if the inequality actually reverses when you have concave functions. Okay. Now, so this shows you a weakness of expectations when you are comparing variables, because depending on whether or not you have a convex function or a concave function, the results reverse. Okay, now if you have, so this is my humble contribution. If you have a concave increasing function, we can show with a phi of 0 equal to 0 that expected phi of the sum of the TIs, the dependence, less than or equal than E over E minus 1 expected phi of the sum of the YI.
May I ask you, how come Poisson distribution comes into this inequality?
What?
How Poisson distribution appears in this inequality?
How the distributions appear?
The Poisson distribution comes.
Oh, well, the Poisson distribution comes in the proof.
Can it be replaced by binomial or something?
Well, what happens is the Sharp constant, the Sharp inequality is with the Poisson. If you replace by a different random variable, you don't have Sharp constant. You don't have Sharp inequality.
What do you mean by sharp?
That means that at least in the limit, there is a distribution, there is a set of these that for which this in the limit is an equality. Now, notice that for this it results, if we go down, okay, so this is an inequality that I just published. And the reason why, I don't know if E over E minus 1 is sharp, probably not. But the reason why I present it to you is because I have a sharp inequality that has the same constant. So that gives me some hope. So now notice that if phi of x is equal to x, it is both convex and concave, then the expected value of the sum of yi is equal to the expected value of pi of 1 times the expected value of the sum of the d sub i's, which is equal to 1, and they end up being the same. So you have an identity. Okay, so I guess I should have put here d sub I, because the expected value of the Poisson of 1 is 1. Okay, so again, everything goes back to linearity of expectations. Now, the second, in my thesis paper that was published in 1990 in the Proceedings of the American Mathematical Society, I proved this inequality. So take P between 1 and 2. Then the LP norm of the sum of the D sub i's, the martingale difference sequence. So now it's martingale difference sequence is less than or equal than a constant times the LP norm of the sum of the independent variables. Now, so anyways, is there any question about what the inequality is doing? I'll tell you why it is easy to replace martingale difference sequences by independent variables. So let's assume that P is equal to 1. So we go down. Okay. Okay, so you see, okay, so now the inequality is stronger. You have the expected value of the maximum of the sum of the D sub i's less than a constant times the expected value of the sum of E sub i's, reminding you of Levy's inequality. Okay, but this works for P equal to 1 as well. It doesn't, you don't need to have, because Burkholder-Gandhi works for P bigger than or equal than 1. Okay, now the proof sketch, I'll give you a preliminary of this, and then I'll show you exactly how it goes. The proof sketch is first use Burkholder-Davis-Gandhi. So if I use Burkholder-Davis-Gandhi, I take these two squares. Okay, then you use the decoupling inequality for concave functions to decouple. And then I use Burkholder-Gandhi back to get the y's. Okay, this is not the proof that I used, but it's similar. It was a little more complicated, but now that they have done that, I can just invoke it.
So Victor, in that inequality, the maximum is taken over subsequence from
Oh.
I equal 1 to j, not n.
This should be J.
Okay,
The way
Thank you.
up there in the
Up
in the summation, right? The sum.
Oh,
From I to
yeah,
1
yeah,
to
this
sure.
should be J,
J, okay.
J going
Okay,
forward.
right, right.
Thank you.
Okay.
So you caught me.
Yeah.
I try so hard to avoid, but that was.
Okay, no, but I was trying to understand that, but now.
Okay, okay. So now, let's go to the next result. This is a result for this conference. So you have arbitrarily dependent variables, and here you have the probability, the tail probability of this is less than or equal than E over E minus 1 tail probability of the sum of the independent variables, bigger than T. And this constant is sharp. This is whatever he said, an observation. So it's an observation. The proof follows by an optimization argument, okay? So you see it's the same constant, but in this case, one can show that it is sharp. Now, let me show you an application to show that this is actually useful. So suppose that you have an insurance company and you want to get a bound on the worst expense that you acquire, that you get. So suppose that you want to find the T of alpha D such that this is less than alpha, okay? It's like the value at risk. Then this can be calculated by first calculating this particular value of the quantile or the value at risk of the independent variables. But this is much easier to do. And the T value that has this property, so you can do that. The T value that is less than or equal than E minus 1 over E alpha is going to give you this. Okay? So this tells you, if you're an insurance company, it tells you how to price your insurance in order to, or how much reserves you need to protect yourself against the worst case scenario. Okay, so now let's go to the next. That's just propaganda. So let's go to the next, and those are the references, they are in the file, but let's go to the second.
I will put them online on the site of IHP after.
Huh?
If you don't mind, I will put all those things online in the site of IHP.
Okay, of course. So I have to add one reference, which is the reference to
But
AIHP.
this is the end of the slide, I think.
Excuse me? No, but go to the others.
To the other notes.
Yeah, because that one is also related to what you guys do. Because, so suppose that you have a sum of a martingale, which is stationary. Okay? You have a stationary martingale, and you want to bound the L1 norm of that. Okay? The same, okay, so this is your martingale, different sequence, stationary. Then you use the Burkholder-Gandhi, there's a constant one. I don't know what the sharp constants for Burkholder-Gandhi is. I tried to find it, but nobody told me. Then by decoupling, you get a second constant. And then you use Burkholder-Gandhi again, the other side, to get this. Okay. And so now, then this is less than or equal than 2C1, C2, C3, Ck times Ky of n. Where K is, this is where my advisor comes in. K is a function that gives you the L1 norm or the LP norm of a sum of independent variables. So you have the integral of a multivariate integral of a sum of x sub I, y sub I to the p, and the K function reduces that to one function, okay, that you can calculate. Okay, so let's see. So now let me show you how to calculate it. The inverse to the KD inverse of Y, which is the same because the distribution of D is the same as the distribution of the D sub I is the same as the distribution of
Is there?
Y sub I.
That's the only page in this file.
Excuse me?
That's the only page.
Yeah,
Okay.
this is the end of the proof. So I'm just showing you how to get this. And so if you have stationary variables, okay, and you know the distribution of one of them, you basically can get the order of magnitude of the growth of the L1. And I asked Bruchholder once, because Bruchholder got the square function inequalities. I asked him, do you know what the growth rate of the martingale is based on that? And he said, no. I said, oh, good. So anyways, that's the end of the talk.
Okay.
And this is the one that want us to find an application for.
Constants, the Sharp constants and applications. Yes, because you work with stationarity.
Okay.
I don't. This is just a special case, but when you have stationarity, you might be able to find the Sharp constant and maybe an application. Okay?
Il y a une question de l'extérieur.
Excuse me?
There is a question from.
Sorry,
distance.
I didn't see.
Let's see, the last transparency.
Can you please explain? Why did you have the relation between sharp inequality and sharp ratio?
Sharp inequality or sharp ratio, what does that mean?
I don't know.
Well, which inequality?
I guess in your self-normalized ones.
Oh, the
I
self-normalized.
guess so.
Well, if you have the inequality, which is sharp, it means that the constant is best possible. If you take the ratio, the constant remains to be the same value. I'm not saying that if you take the difference, you get something. That's a different animal.
Maybe no, it's not this one. It's the other one. Where is it? Yes.
Now, the journal where the maximum appears, 12 years ago, I have a paper with TLI where we prove the constant of 2 for the maximum. And this year, just a few months ago, appeared the Sharp constant. Okay, so it took 5 years for the journal to agree, but finally and we have applications to political science and economics. So that, because that's an observation. It's these easy things to do, which you could do it in 5 minutes.
And I think I was thinking it was this one, but okay. No more questions, maybe?
This inequality on the last slide for maximal is very surprising. I mean, dependent on the left-hand side and independent on the right-hand side.
I mean, the very last one?
But this is not very
No.
surprising. From the
It's
point
not,
of view-
as I said, it's not very surprising once you know what the inequality is. The thing is,
No, I don't mean the concept.
no,
I
no,
don't mean the concept, but in general, it is known that the maximum of independent random variables are extreme. Simple,
That's
it's
right.
known independently of the structure.
No, dependence is not important in maximum inequalities.
No, it's not maximum inequality, it's for maximum, so this is a special maximum on the left, maximum on the right, yeah? There's not a maximum that you have maximum on the left and some, you forget about.
now, good, that's a good remark. Because in the other type of decoupling, you have two-sided inequalities for max. Okay, so on this decoupling, you just have the upper bound, but on the other decoupling, you have two-sided inequalities. And I could give you references for that. Wapin and Wyszynski proved that. I have a refinement or a sharpness of one side, but so if you're looking at maximums, maybe you should learn decoupling. Because it gives you two-sided inequalities. So if you have a time series, you're looking at the maximum, you can decouple a time series and then get information. Or if you have a sequence of independent variables up to a stopping time, you can decouple the stopping time and then everything breaks down. And the last thing is, I work at Columbia University and Abraham Wald founded the department. One of the things that I have done is work in Wald's equation, and Wald's equation is also a decoupling equality. So anyways, that's a lot of propaganda, I'm sorry.
Okay. So you are playing football, so that's good. So that's for me, thank you very much.
Yeah, exactly.
So it's
Final
very
football,
dedicated.
just for you.
It was, in fact, that makes me remember once I was in Torun and I was obliged by a group of very strong people from Poland who obliged me to see my first football contest.
France goes to Brazil.
Yeah. But I didn't have the choice. They were definitely stronger than me.
I asked you to get tickets for me. To
Yes,
see
but
Messi.
I told you I really, that's not my.
No, but like we don't say this thing
Excuse me?
in France now. We don't speak about Messi anymore. We
No.
don't talk about this player since.
He's still doing well.
Yeah, but since the final of the World Cup, we don't like Argentinian anymore. I'm kidding.
Oh, okay.
Okay. So I think that there will be a good discussion. So thank you.
Just joking.
That's okay.
So thank you for coming. That's good to see you again after several years. So I let you speak maybe.
Okay. Thank you very much, Paul. It's always a great pleasure to participate to the event organized by Paul, who is my first co-author in my whole life. So I remember that. And so Paul asked me, told me about the topic and time series, and I just mentioned Hawkes processes, and Paul asked me if I can do like maybe kind of a general overview talk about Hawkes processes, which is what I'm going to do here. So I'm going to talk about Hawkes processes and also connection to finance. That's going to be related to your talk actually, in a kind of a loose way, and just for the end, because it's the last talk, and to speak about something a bit more, funny, or I don't know, like just talk a bit about football and connection, but this kind of point processes and football. Yeah, so Hawkes processes, I guess you all know about Hawkes processes. So they are point processes, and so that you are just modeling here a sequence of random events. And the specificity of Hawkes processes is these self-exciting features, which mean that if you look at the intensity at time t, so if you want to forecast the probability that there is an event between t and t plus dt, it's going to be mu dt, which is the Poisson part, n, which is like so-called base intensity, and you get this sum of phi of t minus ji, and the ji are the location of the past events. Okay, so typically phi is going to be a decreasing function. So basically, you at time t, you're looking at the location of the event in the past, and you look at the t minus ji, and so you are adding up the sum of the phi of t minus ji. Which means that if you have a lot of events in a recent past, while t minus ji is going to be small for many i's, and so since phi is typically decreasing, phi of t minus gi is going to be large for many I, and so this sum is going to be high, and so intensity is going to be high, and so it's very likely that you're going to get an event, right? So this is why these events are called self-exciting, and as if you look at the book of Daly and Lear-Jones, they say that actually these Hawkes processes, they play the role of autoregressive processes, but in the world of point processes. Okay, so they make the connection like IID process for point process is kind of the Poisson process, and autoregressive for the one processes. Well, if you look in the point process world, it's going to be like Hawkes processes. So they get these nice self-exciting features, and actually they have been introduced by Hawkes in 1971. And actually, if you discuss with Hawkes, he's going to tell you that he has just introduced that just from a mathematical viewpoint. But very soon after the introduction of Hawkes processes, a colleague of his that is called Hawkes with an O and not with an H used it for earthquakes, right? So often you can read that Hawkes processes, they have been introduced to model earthquake. Actually, it's not true. It's just the colleague of Hawkes who thought about these processes to model earthquake. And it's very natural to model earthquakes because if you think about it, you're going to model the earthquakes and then the aftershock and then the aftershock and then the aftershock. And so, of course, if you have an aftershock right now, it's very likely that you get another one in the next minutes. And if you have a lot of aftershocks, it's even more likely that you're going to get a new aftershock in the next minute. And if you didn't have any aftershock for quite some time, the probability that you get an aftershock is going to be small. So, I mean, these much self-exciting processes, they are very well adapted for that. And nowadays they are used in many different fields in applied math. They are used a lot in neuroscience, in network analysis, in criminology. So there are some interesting papers about criminology and Hawkes processes. So basically what they do, I mean, just as an example, they look at robberies in Chicago. For example, they have a database of robbery in Chicago. And they look at what's the likelihood that you're going to get a robbery in your house, given the past robbery that you have seen in your neighborhood, and they fit Hawkes processes on that, and it's quite efficient actually, because it's really like, I mean, intuitively you really see that there is these self-exciting features in the robberies, right?
But this intensity can explode to infinity in a time.
So yeah, we're going to talk about that just in next slide. It's going to be one of the crucial points here. And yeah, so it's used in neuroscience, network analysis, and also in finance. We'll talk about it. Okay, so just as an example of the intensity of the Hawkes process, so you have the base intensity, this is the Poisson intensity, and then you have the first jump. So when you have the first jump, I mean, your intensity jump by phi of 0. Okay, so you're adding phi of 0 here because there is a jump, so t minus gi is equal to 0. And then it decays, and then you have a new jump, so you add phi of 0, and it decays, you have the jump. So this is a typical graph of the intensity of a Hawkes process. Okay, so just before coming to your comment, Donatas, just on why are Hawkes processes that popular these days? So first, because as you can see, there is this connection between this, I mean, autoregressive processes in the conventional time series world and Hawkes processes for point processes. So it's a natural, I mean, if you know about time series, it's a very natural extension of Poisson processes. Okay, so this is kind of the mathematical explanation, but there is another explanation why people are interested in Hawkes processes in modeling is because of the underlying branching structure that you have in Hawkes processes. So the branching structure is quite simple actually, and we have to do it so we're going to assume that the L1 norm of phi is smaller than 1. And it's coming back to your comment, Donatas, this condition here ensure that you get stability of Hawkes process. So here it becomes a bit tricky. It's more tricky than with conventional type series. When I say stability here, it's a condition that ensures that you get an ergodic intensity. Okay, so with this condition here, you know that you can get an ergodic solution for the intensity. If you just want to avoid explosion of your Hawkes process, the only thing that you need is that this guy is locally integrable. So there is often a bit confusion about this. We call that stability condition. So this is an ergodicity condition, and basically I'm going to use this ergodicity condition all the time. But even you can have this condition that is not satisfied, and still the process is not going to explode. So we have the intuition that Hawkes process can explode because it's self-exciting. So if you have like plenty of events, there are going to be even more events and so on and so on. So it could explode. But the non-exploding condition is just this guy to be locally integral. So, but we're going to assume that, okay, this L1 norm of phi squared on 1. And then I'm just going to explain this branching structure underlying Hawkes processes. So the way you do to see that is that you imagine a population, okay? You take a population, and in the population, you have some migrants coming. And the I did the same mistake. Sorry for that.
Non, tu fais, tu tapes 2 fois.
Encore, jusqu'à ce que ça revienne.
Again?
Okay, je touche plus. So in this population, you have migrants coming. Okay, and the migrants, they are coming into the population as a Poisson process, classical Poisson process with parameter mu. Okay, so the migrant, they come into the population as a Poisson process with parameter mu. And the migrants, once they're in the population, they have children. Okay, and the children of the migrants, they are coming into the population as a non-homogeneous Poisson process with intensity function phi. Okay, so you have the migrants coming, Poisson process with parameter mu, and the migrants, they have children as a non-homogeneous Poisson process with intensity the function phi. And the children themselves, they have children as a non-homogeneous Poisson process with intensity the function phi, and the children, the grandchildren themselves have children, and so on and so on. So you have two types of individuals. You have the migrants coming into the population as a Poisson process with parameter mu. Then these guys, they have children coming as non-homogeneous Poisson process with intensity phi, and all the children themselves, whatever the generation, they have children with a non-homogeneous Poisson process with intensity phi. And if you do that, you define the same Hawkes process. Okay, so we see again this condition integral of phi smaller than 1 is kind of the same condition as in Galton-Watson.
Can you say something more? Can you please switch to the next slide? Why?
Yeah. This one. Yeah, okay. And so you see that this condition in L1 norm of phi smaller than 1 is the very same condition as what you have in Galton-Watson. In Galton-Watson, you need that the expectation of psi is smaller than 1. And if you want, you can see a Hawkes process as a Galton-Watson with delayed birth. So instead of Galton-Watson with everybody like just is born on the same day, like a Hawkes process like Galton-Watson, but the children they don't get born at the same time. I mean, they take some time, and this time is given by this non-homogeneous Poisson process. So really, Hawkes process, you can see that a Galton-Watson with delayed birth. You can really see that. And yeah, so I mean, just because I'm going to give you the example of finance, but why we like that this interpretation in finance? Because often we like to consider in finance that there are two types of transactions, two types of orders. You have the people that buy asset or sell asset just because they have like fundamental reason to buy. So these people, they come like randomly on the market. They come from time to time, they buy and they sell. So these are the migrants, basically. They come from time to time to the market. And you have all the people that are just like screening the markets. I mean, just looking at the markets with algorithm and just reacting to what they see on the market. And these are all these people who are doing transaction just because they have seen something on the market. So they are just reacting to something that they have seen. So their transactions are just triggered by some other transaction on the market. These guys are the children, basically. They are the children. It's very natural because they are just here because there were another transaction before them. So it's a very natural dichotomy for finance. You have read the fundamental orders, fundamental transaction, people coming randomly on the market because they have fundamental reasons to buy or fundamental reasons to sell, and people that are just like reacting, screening the market. And so basically they run algorithm, they have seen something, they analyze past transaction and they just react to past transaction they have seen. So which means that their own transaction are just going to be triggered by past transaction, and I mean they are the migrants. Okay, it makes a lot of sense.
So the Hawkes process here measures just the number of transactions,
yes,
not
yes.
what the,
no
the value.
Exactly. No, here just at one. If you think about finance, just 1.1 transaction rate. So no value, no value here, and no volume. I mean, I'm assuming that everything is the same.
No, children are independent and completely.
Sorry?
Children are independent, coming from different migrants.
Yeah, I mean, if you start from a new migrant, if you start, it's like it's a new independent Hawkes process. It's a new independent. The thing is that if you just observe your point, if you just, I mean, from a statistical viewpoint, if you take your point, you cannot say who is the migrant who has triggered this point.
So the question, my question, if this whole process can be viewed as a Poisson process.
No, because it's no, because it would be because it's really you have the non-Markov features.
Yeah, you left something from each Poisson point for calling mark, and these marks are independent according to some law.
You mean like Poisson cluster, for example? Like yeah, you can really see it as a Poisson cluster. I mean, you have 1 point, you have 1 cluster. You can basically it's almost like a renewal where you like gonna separate all these families that are generated by one migrant. Actually, we're exactly gonna use this separation on it.
Right.
Coming back to this, so this condition that this L1 norm of 5, so it's a super important condition when you study the Hawkes processes. I told you why, because it's the condition that guarantee ergodicity. But in the literature, it's called stability condition, and it has been used also for something else, which is the following. It is that if you take a family, so I'm coming back to your comment, so if you consider a family, so what is a family? It's one migrant, the children, the grandchildren, the great-grandchildren, and so on and so on. So each migrant, he has on average L1 norm of 5 children. He has on average L1 norm of 5 square grandchildren, and on average N1 norm of 5 to the power 3 grandchildren. So if you look at within a family, the proportion of descendants versus the size of the family. You have the sum of this L1 norm of 5 to the power k divided by the sum of the L1 norm of 5 to the power k plus 1. This plus 1 being the initial migrant. So here I'm just computing in a family the proportion of people that are descendants and non-migrant. It's the sum of L1 norm of 5 to the power k divided by the same sum plus 1, because in the family you have all these descendants plus 1, which is the initial migrant. And you do this computation, you're going to get L1 norm of 5. So in terms of modeling, the L1 norm of 5, we said that it represents the degree of endogeneity of your population. Okay, so degree of endogeneity is the number of people in the population that have been generated by other people and that are non-migrant. So from a financial viewpoint, this L1 norm of 5 is the proportion of endogenous order. Okay, so it's the proportion of order that are just triggered by other order and that are non-fundamental. And you can get that because of this Poisson cluster. Okay, so now I'm going to talk about something that seems totally different, and then so that's related to your talk, and then I'm going to make the connection with the Hawkes process. So now I'm going to talk about volatility. So as you see, Paul, I'm doing this for you. We do finance and football, your two favorite topics. So now I'm going.
Yes, that's good for a conference on ecology.
We started studying volatility together, if you remember. Yeah, but we are doing green finance. Okay. So now I'm going to talk about something that seems completely different: continuous time finance. Okay, continuous time finance. We like to model the price of assets by Ito processes. Okay, so just P is the price of your favorite stock in dimension 1, and I'm modeling the price of the Ito process. And when you're interested in risk management, or when you're interested in options or derivative, we know that the important process to model is the volatility. Okay, so we want to model the volatility. And well, how can you model the volatility? Well, the simplest thing you can do is just to say the volatility is constant. Okay, and then this is the Black-Scholes model. Or you can say the volatility is itself an Ito process, and in that case, you have the so-called stochastic volatility model. And you can do like, there are like many famous models in the literature. But there is something interesting is that if you look at now the volatility sample path that you get from this model, so if you take Black-Scholes or if you take stochastic volatility, basically what you get is that either the volatility is very smooth, okay, like it's constant in Black-Scholes, or it's infinity because you have like time-varying version of Black-Scholes where you put some exponential function or something like that. Or you get a volatility that is non-regular, but is non-regular like a Brownian motion, because it's Ito processes, so it's basically time change Brownian motion. So you have like some non-smooth volatility, but non-smooth in a very specific way. It's like non-smooth like a Brownian motion. And the question is like, well, I mean, there is no reason to impose that, so we could be interested in having like further classes of volatility. And actually to do that, well, there's an easy way to there's a nice process that you can introduce. And again, Paul, everything is coming back to you because this is something that I've heard from you the first time. Why not having the volatility as a fractional buoyant motion? There is nothing in financial theory that prevents you to have the volatility that behaves as a fractional buoyant motion. So I know that in this audience, I don't need to define the fractional buoyant motion, but basically what we're going to do, just to allow a wider range of smoothness for the volatility, we're going to allow this guy to be fractional type. Okay, so we allow the volatility to be driven by a fractional buoyant motion. And what we want to do is to check on data whether it makes sense or whether it does not make sense. So just as a reminder, I mean, you all know that the fractional buoyant motion is parameterized by this Hurst parameter that is between 0 and 1. And as you know, the Hurst parameter is giving you the smoothness of the fractional buoyant motion, right? So if you have fractional buoyant motion with Hurst parameter h, the smoothness is h minus epsilon. So h is really the smoothness of the fractional buoyant motion. And just as a quick reminder, I mean, just for the form of the fractional buoyant motion that I'm going to use, I'm going to essentially use that the fractional buoyant motion, it's essentially this integral of a classical buoyant motion with this Volterra kernel here. Okay, so I'm mainly going to use this representation of the fractional buoyant motion. Okay, so the goal here is to, as remember, the goal is to model this. Okay, is to model the volatility. Okay, we want to model the guy. And what I'm plotting here is the graph of the log of the volatility of the S&P index, which is the major index in the world, and over almost 10 years. Okay, so over more than 10 years, here you have the graph of the log of the volatility, and I put 1 point per day. So every day I measure the log of the volatility, I just put 1 point per day, and you have this graph.
Sorry, but it's the log of
historical volatility. Yeah, thanks for the, sorry, I should have said it. It's not option here, it's just historical vol. So it's like every day at 11 o'clock, I have a good estimator of volatility. Every day at 11 o'clock, I measure the volatility, and this is the graph. And the goal of this graph is just to show you that I guess none of us would model that with a buoyant motion. And none of us would use a model motion to model that, and it definitely looks much more rough, much rougher than a classical buoyant motion. Okay, so it gives us intuition that the log volatility seems much rougher than a classical buoyant motion. So how can I check that? Well, I'm going to do what we classically do in this case. What I'm going to look at is to look at the behavior of the log volatility increment. Okay, so I'm going to look at log volatility increment over 1 day, 2 days, 3 days, 100 days. I'm going to look at the average behavior of the log volatility increment to the power q. Why do I want to do that? Because, I mean, if it's a fractional buoyant motion, I mean, this guy should behave, of course, as delta to the power q times h, right? So I'm going to compute that for various q, and I'm just going to look at the regression of this guy with respect to delta to the power something. Okay, so I'm going to show you the log of m against the log of delta, and I want to check whether the log of m is proportional to the log of delta, right? And I'm going to take delta going from 1 day to like 200 days. And this is what you get. Here you have the log of delta, and you have the log of m, so the different colors corresponds to different q, and you see that really the log of m is really proportional to the log of delta. Delta going from log of delta going from 0 to 4, but actually I can continue to 6, 7, it's still going to be true. So you really have that the log of m is proportional to the log of delta, which means that this guy, m behaves as delta to the power something. And the something is given by the slope of these different lines, right? So now I'm going to look at the slope of the different lines here, okay? And here I'm showing you with respect to q, in blue, you have the different slopes, and in green, you have like 0.14 times q. Okay, so all that to say that these slopes here, they are approximately 0.14 times q, which means that you get this scaling relationship, m delta q behave as basically delta to the power 0.14 times q. Okay? So this is the first thing. We have this kind of scaling relationship of the volatility, log of sigma. I mean, this expectation behave. I mean, it's not an expectation; it's a sample average. This m delta behave as delta to m delta q behave as delta to 0.14 times q, and then I can show the histogram of the log volatility. So here, I mean, this is something that is very well known in financial econometrics, that log volatility is more or less Gaussian. It's not part of a Gaussian process. So we just retrieve that the log of the volatility, I mean, it behaves as a Gaussian process. So you put that together, you have that the log volatility behave as a Gaussian process, and you have that this scaling relationship that is true with like S around 0.14. So I come back to my NSA lecture note with you, Paul, and there's just one Gaussian process that satisfies that fractional Gaussian motion. Yes.
Need something, the histogram and the overlay curves. How does that show that it's close to Gaussian?
So because here, I mean, I'm not talking too much of the center part, but if you look at the tail, it's pretty reasonable. And what I'm showing here, so you have the histogram, okay? In blue, you just have the Gaussian fit. I just measure like average and standard deviation, and I'm looking at the Gaussian. And what you have in red, so for a lag equal to 1 day, the blue and the red are the same. And what I have here, I'm just I'm just doing the scaling of the red curve with the 0.14 here. Okay, and what you can see is that if you scale the red curve with the 0.14 here over 5 days, 25 days, and 125 days, it's almost like the blue curve. So just showing that you have this like fractional scaling that seems to fit all the time. Right. I agree with you that it's not like perfectly Gaussian here and here, but I mean the tail are reasonably good. So again, I take my lecture note from a long time ago, and I obtained that log volatility essentially behaves as a fractional bond motion with first parameter equal to 0.1, around 0.1. So when I say of order 0.1, it means that, I mean, you can take any reasonable asset, we'll always find that the log volatility behaves as a fractional bond motion with a Hertz parameter, let's say between 0.05 and 0.2. So we say around 0.1, but it's really like around 0.1. Yes.
It should be stationary or non-stationary, this fractional bond?
Not. It's
non-stationary.
definitely not stationary.
Yes,
So it's a very, very good point. That is, I mean, I know in this audience is great because I don't need to everybody understand that immediately. That I really believe that log volatility is not a stationary process, but since the Hertz parameter is so small, it's not a big deal because I can still model that with a fractional motion because my increase, my low is like in t to the power h. H is close to 0. So even for 10 years of data, the model is still going to remain reasonable. Of course, I mean, I cannot model 1000 years of data with that, but since H is so small, it's non-stationary, but the model is not going to be crazy because my scaling is in t to the power h. And H.
But there is a range of the parameters for which the process is defined, the stationary or non-stationary.
I mean, here, I'm just saying log volatility is a fraction. I mean, you will see that in the end, I'm going to use a formally stationary version, but the stationary t is not, I mean, the key point here, because really for me, the key point that h is very small. So I can very well say the log of volatility is just a fractional bond motion. In that case, it's really non-stationary. I mean, for any h is non-stationary, but the h is so small that it kind of acts as stationary. Just because the h is very small. If you look at reasonable time scales, if you don't take time too large, it's kind of like it's stationary. In the end, we're going to take a formally really stationary model, but really, I mean, the fact that h is small means that you don't even need to take.
Because you said that there is with as parameter or model 0.1. This was
yeah, exactly. So really like really non-stationary, okay. But the way the laws are changing with time is extremely slow. And it's so slow that you can consider it. And so with this very simple model, in fact, you can retrieve most of the stylus facts and property of historical volatility. And plus, you can, if you are interested in option and implied volatility, you can also reproduce the behavior of implied volatility surface. So it's quite interesting in terms of risk management. Okay, so what do we want to do now? We want to understand why it's true. Because what you obtain is that, so many studies have been done on this topic, not by us, by other people, and you systematically obtain the function that volatility is rough. So we said that volatility is rough in the sense that the sample path is rougher than that of a classical bond motion. And systematically you obtain that volatility is very well approximated by, if you take that, you sample, basically volatility is very well approximated by sampling a fractional bond motion with a Hertz parameter of order 0.2. Okay. So of course, I'm not saying that the volatility intraday is like a fractional bond motion, but you take a fractional bond motion of order 0.1, you sample it like once per day. It's a very good approximation of your log volatility. And it seems to be always true. So we want to try to understand why we always find this result. It has been found on more than 10,000 of assets. And so we want to understand that. And yeah, so this is something that seems to be universal. So if you have something universal in finance, it should be kind of related to some no arbitrage concept. And this is this thing that we're going to try to do and make with the Hawkes processes. So this is going to be my second part. Don't worry, I don't plan to talk about all this. Okay, so now we're going to do like basic finance, and that is like really the fundamental of finance, and that's going to give us the key on the way the volatility is behaving. So actually, we're going to talk about market impact. And market impact is just something very simple. It shows the fact that it's not only in finance, it's like in potatoes or a car or whatever. When you're buying, you're pushing the price up. When you're selling, you're pushing the price down. Okay, this is the so-called market impact. When you're buying something, if many people buy, it's pushing the price up. Many people sell, it's pushing the price down. It's like housing, apartments, whatever. And here, I mean, we're going to be interested in the market impact function of so-called meter orders. So what are meter orders? These are the orders of people buying big quantities. So for example, your French state or big insurance, something like that, they come to the market and they say, I don't know, the French state needs to buy 50 million shares of something. Okay, 50 million shares of bonds, for example. Or you have your insurance needs to buy 50 million stocks because, I mean, they are insurance, they need to cover their risk and things like that. So if you need to buy 50 million stocks on the market, you're not going to do it in 1 second. If you need to buy 50 million stock, you're going to take the whole day to do it, for example. So you're going to buy like 10,000, you're going to wait by 10,000 again, you're going to wait by 10,000, and maybe at the end of the day, you will have bought 50 million stocks. Okay, so this is what we call meter order and meter order splitting. Like you have a giant order and you split this order over the day. Right. So this is what we're going to do. And basically, what we're going to be interested in is this market impact. So what is the market impact? Is like this is time. Okay, and these are empirical measurements. So my meter order splitting starts here. This is the morning. I'm buying, and I'm ending my trading here at the end of the day. Okay, so you see on average, so these are average of a million of meter orders. On average, this is the price. I'm pushing the price up because I'm buying. I'm pushing the price up. Then I'm done, and then the price is going to revert to some level. Okay, very standard stuff. Like again, it's like if you think about people buying apartments or whatever, it's the same phenomenon. So you have two parts in the market impact. You have what we call the transitory part of market impact, like when you're buying, you're pushing the price up while you're buying, and then you have the relaxation here. And I'm going to be notably interested in this point here. What happened when T is very large? Sorry. When T is very large, we call that the permanent market impact. So what is the permanent market impact? It's you have bought 50 million shares. A long time after this, what is remaining of the fact that you have bought these 50 million shares? What is the information on the market, on the price remaining of these 50 million shares that you have bought? Okay, so this is the so-called permanent market impact. This is the trace of your transaction on the market after a long time after completion of your order. Okay, so this is really the information that you have conveyed to the market, because this is just like the market reacting here. The market is reacting, and then it relaxes. And a long time after your trade, I mean, what is remaining of your trade? This is the permanent market. And you have a simple result that tells you that if your market is efficient, basically, so market being efficient in a statistical way, which means that you cannot like buying, pushing the price up, then selling, pushing the price down, buying, pushing the price up, selling, pushing the price down, and make money out of it. If the market is efficient, your permanent market impact should be linear. And actually, this is kind of obvious because it's just saying that it should be the same effect. Buying 50 million shares in 8 hours should be the same effect of buying 25 million shares in 4 hours and 25 million shares in 8 hours. So the permanent market impact should be linear. Okay. And I mean, you can prove that, and there are people who have proved that in a much more mathematical way. But basically, the market impact is linear, which means permanent market impact linear, which means that if Paul, you buy 50 million shares, you're going to move the market price on the long run by constant time 50 million. It's linear. So now we're going to do something very stupid and very simple, just doing accounting. So I'm just saying that knowing that the permanent market impact is linear, and I'm assuming that all what I have on the market is people doing meter order. What is the price at the end of the day? The price at the end of the day is the sum of all the impact of my buy meter orders. So you have the P. So for example, here the is buy meter order as a volume VIA. So you have the impact, which is K times VIA for all the buy meter order, minus the impact of all the sell meter orders. The buy meter order are pushing the price up, the sell meter order are pushing the price down. You have NSA buy meter order, NSB sell meter order. And so the price at the end of the day is just the sum of all the impact plus the martingale part, because the impact is the average move. Okay, so the impact is an expectation, so you have this martingale. But let's forget about the martingale. Okay, so it's very simple. The price at the end of the day is just given by this. Okay, and what is this in the end? This is just the total volume of buy order and the total volume of sell order. So I'm just counting how many stocks have been bought at the end of the day, how many stocks have been sold at the end of the day. Just my price is a constant and the difference between the two. It's just offer and demand equilibrium. Okay, my price is just based on the difference on the offer and demand. Okay, so this is my price at the end of the day. So my first, so you see no assumption for the time, almost no assumption. Now we're going to make one assumption. We are all been a bit used to mathematical finance and so on. I'm going to assume that the price is a martingale. Why is the price in the martingale? Means that I cannot forecast, basically. I cannot forecast the price, I cannot forecast return. We know it's reasonably true that I cannot do forecast. Okay, so if my price is a martingale, my price should be the conditional expectation of my price at the end of the day. Okay, so I have this equation for my price at the end of the day. So my price now should be the conditional expectation of the price at the end of the day. Okay, so my price is a martingale. So my price at time t is a conditional expectation of this price at the end of the day. Okay, because I don't put this martingale here. And so finally, what you have is that the price at time t is just given by this guy. And if you think about it, it's very natural. So what this equation telling you is mean that you are time t and you are all traders at time t. You are traders at time t, what are you going to look at? You look at the past buy order coming starting at minus infinity to time t. Okay, the past buy order, and you do a forecast of what's going to come. Okay, and basically this is telling you that the price that is on the market is your forecast on the long-term imbalance that you're going to have between buy order and sell order, which is quite natural. I mean, if you forecast that they're going to be on the long run a big difference between the total amount of buying and the total amount of selling, the price will reflect that. And again, it's like when you buy apartments. And if people forecast that the price of housing are going to crash, they're going to move the price. Okay. And why the price is moving in this case? Because each time you see a new order coming, okay, each time there is a new order coming to the market, you're going to revise your conditional expectation. Because if you see like a lot of buy order coming, you're going to say, okay, there's a lot of buy order coming. There are self-exciting features. So I think that there's going to be more buy order coming to the future. So you're going to recompute that and you're going to change it. Okay, so it's really quite simple in the end. It's just telling you that the price at time t, it's your forecast of the total imbalance of buy order and sell order between minus infinity and plus infinity, basically. So all what is between minus infinity and now you know it, but then you have to do some forecast between t and the future. And this forecast you do it based on information that you get. And the information that you get is just the order coming. It's like when you do, I mean, if you buy a house, if you're going to look at the transaction, the recent transaction of houses, and you're going to revise your price based on what you have seen on the newspaper about the recent transaction. Right? So it's very simple. Okay, so now we're almost done. I mean, some sense, because this is nice, but this is really theoretical. Okay. Now I just need to compute that. Okay, I just want to compute PT. So to compute PT, I need a model for that. I need a model for the number of buy order between minus infinity and long time for me, and I need a model for. I want to compute it. And I know statistically that Hawk's processes are very good to model order flows. So the only thing that I'm going to do now, I'm going to model this guy by a Hawk's process, and this guy by a Hawk's process. Okay, no other assumption, just Hawk's processes, because I know that statistically they fit order flow very well. So I'm going to model this guy by a Hawk's process, this guy by a Hawk's process, and I'm going to compute the conditional expectation.
What about a function phi which wouldn't be positive?
You can very well, I mean,
because
what you need
in this case you could get
inhibition.
Difference.
Yeah, absolutely. I mean, the only thing that you need that the intensity in total is positive, but you can have inhibition. You really can have inhibition, and it's a good option for me to advertise the work of Anna Bonnet, because there are a lot of algos that impose phi to be positive, but mathematically speaking, you can have phi negative as long as your intensity is positive. And she did a lot of great, I mean, we have used her algorithm to this thing because they work also for inhibition. So you can very well have phi negative. Okay, as I said, I'm just going to compute that with Hawk's processes. And now I'm going to do something that, I mean, now that I think about it, a lot of things connected to you Paul, in this talk.
So I don't know why I invite you. I should have given the talk.
Yeah, that's true. No, because I'm going to do something, because I'm going to do Hawk's processes. Okay, I'm going to do Hawk's processes, and I don't want to do any assumption on the parameter. And what I'm going to do is that I'm going to consider that this meta order, okay, that I'm considering, they're on a large time interval, right? Because the meta order, they take like 1 day, 2 days, 3 days. So they're on 0t, but I want to say that t is large. Okay, t is large compared to just the time between two typical transactions. So my meta order are on 0t. So this guy is going to be on 0t. This guy is going to be on 0t. And so this guy is going to be modeled by my Hawk's processes. Okay, so I have Hawk's processes on 0 capital T. And I'm going to allow the parameter, and in the end, t is going to go to infinity. Okay, t is going to go to infinity, and I'm going to allow the parameter of my, so I don't want to make any assumption on the parameter. Not making any assumption. I'm going to allow the parameter of my Hawk's processes, which is going to be like the baseline intensity and the kernel. I'm going to allow them to move with t. Okay, which means that in my asymptotic, I can allow my parameter. It's not mandatory, but I just to have like a bigger range of processes, I allow my parameter to move with my asymptotic. And you know, it's close to inner, I mean, the asymptotics on inner processes and things like that. So I'm going to consider Hawk's processes on 0 capital T. Okay, T is like the length of a meta order. T is going to go to infinity. And the parameter of the Hawk's process may depend on T. Okay, and the way they can depend on T, just to have a bit of structure, I'm just going to assume that phi T, the kernel, is of the form AT times phi. Okay, phi is a constant function with integral 1, and AT can depend on T or not depend on T, it just needs to be smaller than 1 to satisfy the stability condition. So I'm doing
processes are going to be independent.
Yeah, just to make things simple here, I'm taking them independent. It can be extended, but to make things simple, I'm taking like bi and cell independent. But as you said, we could have connected to it.
I'm a little lost here.
Sorry?
I'm a little lost by the way you was modeling. For me, the Hawk's, we discussed that 20 minutes ago, is the number of events.
Yeah, yeah.
And here it's a value.
Yeah,
so there's a problem there.
So what I'm saying is that the Hawk's, you see, I want to model this. So basically, I'm assuming that all my transactions, they have the same volume. Okay, and this is the total, thanks for the comment, actually. So you see, this is the total volume that I have observed on the market between 0 and capital S. So I'm just saying that this total volume is just Hawk's process because I'm just assuming that all my transactions have the same volume. So yeah,
all the big banks just doing 10,000.
Exactly. No, they have all the same volume. So basically, I'm assuming that the volume of each transaction is the average volume per transaction. Thanks for the comment. I should have clarified. Okay, we do that, and the nice thing is that something that's going to play a role later is that if you look at beta t. Beta is the baseline of my Hawk's divided by 1 minus EL1 number of the kernel is the average intensity of my Hawk's. Okay, so beta t is the average number of points per unit of time. So the nice thing is that you can compute everything. Okay, so I can compute that, assuming that my process, that this guy are Hawk's processes. I can compute this conditional expectation, and I obtain this result. The preset time t is the integral of, you have a kernel here that appears, dna minus dnb. So these are the Hawk's process of bi order and the Hawk's process of cell order. And this zeta is the explicit function of phi. Okay, so this psi is a convolution of phi, so all that only depends on phi. Okay, so the zeta is an explicit function of phi. What does it mean here? It means that you look at the bi order and the cell order. When you have a bi order coming, your price is jumping by zeta of 0, and then the price is decaying. And if you have a new bi order coming, it's going to jump by zeta of 0. If you have a cell order coming, it's going to jump by minus zeta of 0 and decay. Okay, so this is the way the market is going to, they're going to digest the information that is given by the bi orders of the cell. Okay, so each time you have a bi order, the market is jumping by zeta of 0 and decaying it. And there is something very interesting, I think, here, is that there is something that seems contradictory. Because with the Hawk's processes, you introduce memory. You can forecast Hawk's process. You can forecast the intensity and so on. So you introduce memory, but at the same time, the price is a martingale. So how is it possible? Because actually, and that's why we can do the computation, because the zeta is exactly compensating the memory that the Hawk's processes are putting. So despite that, you can forecast the flows, you can forecast the buy order and sell order, you cannot forecast the price because of this kernel here. Okay, so this kernel really prevents you from forecasting the price. Okay. So this guy remains a martingale. It looks strange like this, but this guy is a martingale. So how do we conclude?
Sorry, and the kernel your psi has to be some concave function or
at this point there is no constraint, but you will see in the end they're going to be a constraint. But at this point, just to make the computation, there's just no constraint. So then let's come back to the meta order. So we see that this is how the market digests orders. So now let's assume that Paul, you come and you do the meta order. Okay, you do your meta order, you buy 50 million stocks. Okay, and some like risky assets. And so Paul, you come, you buy your 50 million stock, and you say, okay, I'm going to buy my 50 million stock between 0 and T. And the way I'm going to do it, I'm just going to trade as a Poisson process. So I have a Poisson process, and each time there is a point of the Poisson process, I'm buying. You do that. Okay, so we are adding you in the market. So this is the market without you. Okay, now we are adding you to the market. So, and we're going to assume that the intensity of your Poisson process is gamma times beta. Remember that beta is the average intensity of the market. So you're doing like, you are gamma beta, so maybe you're doing like 10% of the market. So you're sending your order like a Poisson process, okay? Each time, all order, I mean, thank you again for the comment. All order, they are like the same size. So you're sending your Poisson process over 0 T. If you do that, the market cannot know. If I'm on the market, I cannot make the difference between you and the other people. So all what I'm going to do, I'm going to just apply this zeta function, not only to the rest of the people, but also to you. Okay, I'm just going to digest you the same. And so what's going to be your market impact? This is the expectation of the price move because of you. And this expectation of the price move, I mean, this guy is a martingale, expectation is 0. So the market impact that you have, Paul, is just the expected. It's just given by this. It's just the expectation of this. But this is easy. It's the Poisson process. I can make the computation. I just do the renormalization that I need to do because you're on 0 T and I want to do some asymptotic. So your renormalized market impact, I just keep the computation, is given by this guy. Okay, so this is just the integral basic. Wait. This is just this guy here, and I just do a renormalization. So this is the market impact that you get. And then what I'm going to do, well, I'm just going to take T goes to infinity to see the shape of your market impact in here. And if you do T goes to infinity, you see two things. First, you have this gamma time constant. So you get this linear part. And we know that permanent market impact is linear. So this is the permanent part of the impact that you have here. And there is this guy. And this guy, I mean, you believe that market impact exists because when everybody buys a house, the price of housing is going up. So you want to impose, and I'm coming back to your comment, to impose that this guy converge to something. This guy should not be 0 asymptotically, or not plus infinity. So you're going to impose that this guy converge. Imposing that this guy converge means AT goes to 1. Means we are close to instability. And actually, if you measure like the degree of instability of market, you find like 98%, 95%. So you have to get AT goes to 1 because if AT does not go to 1, I mean, you cannot compensate for this one going to 0. So you have to impose AT go to 1, and then you apply some kind of Karamata theorem that's going to tell you that, I mean, I think you recall if you all are great expert of extreme values and so on. For this kind of thing to have a limit, you know that the limit is necessarily power law. It's like in what's the name of the theorem, the convergence of extreme value in extreme value, like Fisher-Tippett, right? This guy, you know that if a form like that has a limit, you know that the limit is going to be power law. So the first result that you show is that if we just assume that this guy makes sense, which means that if we just assume that we believe that market impact exists, you have no choice. Your market impact, it has to be a power law. Okay, it's a power law plus the linear part. Okay, and because this is really Karamata theorem, right? This is the Karamata theorem that's telling you that when you renormalize, basically they're saying that when we slowly varying function, when you renormalize, it's always a power law. So your market impact, it has to be a power law, and it's very nice because we know that if you measure market impact empirically, you know that its power law is scaling around 1/2. So all that. So basically, we are saying that the market impact is like this. So Paul, you're trading between 0 and 1. You're pushing the price up with this component between 0 and 1, and this component is going to stay. This is your permanent market impact. And you have the transient market impact, this power law that you have mentioned, that is doing that, and then decaying, and in the end, it's going to. So this is the wave market impact. So now it's nice because we know that we have power law for the market impact, and we know that we have no choice. The tail of the Hawkes process should be connected to this parameter here. Okay, again, I'm just assuming that this limit makes sense. So just assuming that this limit exists imply that there is a parameter alpha so that the tail of your Hawkes process behaves like this and the impact behaves like this. Okay, so now I'm coming back to my Hawkes process, to my model. I'm going to take this price model, but now I have a constraint. I know, I come back to your question, I know that the tail of the Hawkes process that is generating this guy, I know that it has to be decaying in 1 divided by x squared 1 plus alpha. I have no choice. I mean, if I believe in market impact, it has to decay this way. The tail has to decay this way, and I know that the alpha is around 0.1, around 0.5. Okay, I know that the alpha is around 0.5 because I know that when I measure the impact curve, it's around 0.5. So I do that, and now that I have this price model, okay, what I can do is that I'm imposing that the tail of the Hawkes process are in 1 divided by x squared 1 plus alpha, and I'm looking at the scaling limit. Okay, so I'm just taking t goes to infinity, I'm just rescaling because this is like a very high frequency model. Now I take t goes to infinity. And if I take t goes to infinity in this model, the result that you get is that the price satisfies this equation. So the price that you get is stochastic volatility. But if you look at the volatility that you get, if you look at this term, if you forget the square root here, it's exactly the Mandelbrot-Warnes representation of fractional motion. Okay, so it's exactly the Mandelbrot-Warnes representation of fractional motion. What is the first parameter? Alpha minus 1. Okay, so I told you that alpha is around 1/2, which tells you that h should be around 0, which is completely consistent. And actually, this is not exactly the fractional motion because you have this square root here. So this is a Cox-Ingersoll-Ross version of the fractional method. So we call this model Raff-Heston because the Heston model in finance is this model here with alpha equals 1. Okay, the square root is a Heston model. So we call that Raff-Heston model because this is a Raff version of the Heston model. And this guy can be made really stationary from a formal point of view, if we want. So all that to say that we have put just assuming that the flow is Hawkes. Okay, this is the only assumption that we have done, and we know it's a reasonable assumption. We have been able to explain the behavior, the rough behavior of the volatility just from this no arbitrage condition, because we have assumed the price is a martingale, and then in the end, we see that naturally, if you assume that the market is efficient, the only volatility that can make sense is this rough volatility. So in some sense, it's a bit, I would say like a disappointing result, or I don't know, but it's just saying that actually, the fact that volatility is rough is not something like very like deep and so on. It's just mechanical. It means that the way the agent they adapt so that they make the prices martingale and so on, in the end, mechanically, the volatility has to be rough. So it's one explanation. I mean, it may be the right explanation to explain this behavior of the volatility.
There's something singular here because if you believe Bouchot,
yeah,
alpha is 1/2.
Yeah, absolutely.
So then
you know very well. Yeah.
This should be logarithmic. I mean, something bizarre.
Because I didn't know that. So this, I mean, you can define all that for h between -1/2 and 1. So this story makes sense for h equals 0. But I mean, if you read the very last stuff of Bouchot, then we say, okay, it seems that h is slightly bigger than 0. So we had a lot of discussion, very nice discussion with him, and it's kind of clear if you look at options on that h is close to 0. But it's a bit bigger than 0.
But I'm lost now. How can the first parameter be negative?
I mean, you have to define it the proper, but so there are two parts in the answer to your question. It's a very excellent question actually. That first, that on data, and even you can talk to Jean-Philippe, he's going to tell that h is bigger than 0. It's like not the order of magnitude is 0, but it's more 0.1 than 0. If you have to pick between 0.1 and 0, you pick 0.1 on whatever. How can you define it? So this is one definition. So the thing that you get is interesting is a case where the volatility does not exist. What exists is just the integrated volatility. So what you get is that your price is a time change per motion. This guy is an increasing process, but singular. So it's an increasing, it's a process that, I mean, it's an increasing process that you cannot differentiate. And for example, you have this kind of equation that defines the volatility. So you see you have xt here, and the weird stuff is you have w time change x here. So you can define it very well. I mean, it's well defined. I mean, weak existence is clear, strong existence is not clear, but you can define it at least as a limit of this. But yeah, so you can go in the hyper route.
So it's a time change Brownian motion.
Yeah.
And the time change is
Not-
slow.
Time change is not absolute. I mean, if h is like smaller than 0, the time change is not absolutely continuous with respect to the back measure.
Oh, so on the contrary.
Yes,
So it has-
Yeah, exactly. It's really like Mandelbrot, you know, like limit of Mandelbrot cascade. Okay, and if I still have like 5 minutes, yeah, I have 5 minutes, Paul. Let's go a bit of that. So this, I mean, for those who are interested in finance, you know that Heston is popular because there is an explicit formula for the prices of option in Heston. Thanks to the connection with Hawks, you can develop an explicit formula for the prices of option in the RAF Heston. So this is something package. Yeah, just 5 minutes about football because I think actually Hawks processes are very adapted to this case. Why? So what we want to do here, and I just have 3 slides, something like that. What I want to do is to be able to say in a football game, I mean, in a team, who are the players who are really creating the dangerous actions? Okay, so because we all, I mean, all of you that are like familiar with football, you say that okay, if you have a goal, the striker is okay, is important, but sometimes the striker is just do nothing. It's just like just the passer and and maybe Messi has done a great pass, and so in that case, you would like to credit Messi. And some other people they say actually this is the second to last pass that is the important one because it creates this equilibrium. So we want to try to find a good metric to define that. Who is creating danger in it? And what are the data we have? We have plenty of data of football games, and these data they are like this, that you take a football game, each time a guy has the ball, you have the location of the guy and what he did with it. So you get like one item each time the guy has it. So what's quite natural in this setting is just to say, okay, I have a Hawks process in dimension 11 player of my team, and each time a guy touches the ball, it's 1 point. Okay, so each time the guy touches the ball, it's 1. And the thing is that if you think about football, I think it's not crazy, it's very adapted, like in the way that if Messi has the ball, it's probably much more likely that Di Maria is going to get the ball soon. Right? So like Messi is exciting Di Maria, or Messi is exciting, I don't know which player. Okay, or Paredes is exciting Messi. You see? So this self-exciting and mutually exciting feature, I mean, besides the joke that this is full, I mean, I think it's very well adapted in football because when one player gets the ball, I mean, it's going to trigger the other players. Okay, and basically you want to find the players that are really playing this. So we take this football data. So each time the guy has the ball, we each time the guy has the ball, we record the points. And actually, what we're going to do, we are going to add 1 dimension. And with this dimension, we call it danger. And what is the danger? Is when the guy has the ball in the penalty box. Okay, so when the guy has the ball in the penalty box, we call that danger. And we want to see basically who is exciting danger. So basically what one says is that when this guy has the ball, it's quite likely that in the near future, there's going to be a danger. Okay, this is how we're going to measure how a guy is important in the football. Okay, so it's quite natural.
It's not very fair for the goalkeeper.
The goalkeeper. I mean, some goalkeepers are a bit better than others. But, no, I mean, it's more like a midfielder thing. But exactly. But you see, like it's natural. Like if you have played football and when you touch the ball, I mean, some guys are running because you are touching the ball, so you are triggering some other guy, like Hawks process. So we do that, and we just, I mean, we're gonna do something simple. So we gotta fit exponential Hawks here, and yeah, again, advertisement for the algorithm of Anna Baudet and co-authors that was like it was very hard for us in the beginning because like fitting this 12-dimensional Hawks process was not working at all, and we were lucky to have discussion with these guys, and thanks to them, we could fit all that. So let me give you some. So how are we going to measure the influence of a player? Think about the population interpretation of Hawks processes. If player I touch the ball, it's going to generate children. But here it's multi-dimensional Hawks, so you have children of different types. So when Messi touches the ball, on average, how many danger does it generate? This is the first metric. Okay. But maybe Messi touch the ball is going to generate danger not at the first generation. Maybe you're going to have danger of grandchildren and danger of great-grandchildren and so on and so on. So two ways to measure your influence in terms of danger: how many dangerous children you generate in the first generation, and how many dangerous children you're going to generate in the whole the generations. Okay, it's very natural. I mean that when you touch the ball, what's the likelihood that they're going to be a dangerous event soon? This is basically what you're saying. And maybe sometime it's going to be a dangerous event because you have touched the ball and another guy has touched another, and they're going to be dangerous. So we're measuring that, and with Hawkes processes, it's like it's just here, right? So what we want to measure is like the integral of phi ij. Okay, it's just the average number of dangerous children you directly generated. And if you just going to compute this guy here, and the ij component is the number of dangerous children across the generation. Okay, very natural. So basically, two measures. If you have the population interpretation, if you are one player, your average number of dangerous children, and if you are one player, the average number of dangerous children, grandchildren, grandchildren, and so on. And this is how we measure if a guy is important, which is I think is fair. Okay, examples. So here, without danger, we took Chelsea 2016-2017. Why? Because Chelsea it was nice because they were always playing with the same 11 players and not changing the tactic. Because I mean the issue is that the guy that changed the players, they change the tactic from one game to another. So to the statistics, it's not very easy. Chelsea, I mean they were just always playing with the same team. So coming back to your comments, if you look at Thibaut Courtois with the goalkeeper, he's excited by himself. Like when he touches the ball, he's very likely that he's going to touch the ball again. But he's not excited at all by the other players. He's 0-0-0. Okay, but you see some interesting stuff. Like, you know, N'Golo Kante, you see, he's excited a bit by Paul, not excited a bit by this guy, very excited by Azpilicueta. I mean, you can measure all that. Okay, so you can measure here, you can measure who is exciting Kante. Okay, and then I'm going to show you a graph. We can show that on the graph. It's more, you see more what's going on. Coming back to danger, here you have the amount of danger directly generated by this player here. So what you see here, if you get the so when I say direct, it's just the first generation danger children. Well, if you look at this, you're not going to be surprised. Eden Hazard, forward player, very good. 22, Pedro, Moses, you're not surprised. And this guy, they are just defenders. If you remember David Luiz from Paris Saint-Germain, and Paris Saint-Germain was very bad. And okay, yes. But what is very interesting is that this guy, Kante, that we all know here, is like a defensive midfielder. Okay, he's defensive midfielder, 0.06. But you see that if you look at the total danger generated, which means danger across the generation of children, it goes up to 0.30. So basically, he's doing as much as Diego Costa with a forward player. So you see that these Hawkes processes, they can help you to identify some kind of non-obvious phenomenon like this one. And if you want to, we can look at it this way. So here is the whole team of Chelsea. So the darker the circle, so this is the total danger, okay, across generation. And the darker the circle, the stronger the danger. So you can see something that if you look at this team of Chelsea, you have two different, the left side and the right side are quite different. You see that basically on this side, it's essentially Eden Hazard. Okay, basically, so it means that they throw the ball to Hazard and all is going to be triggered by Hazard. You see that on this guy, this side, Kante is very important. So the larger the circle is the total intensity received by the guy. Kante is very important, and you have a lot of connection. Okay, this guy is red, this guy is red, this guy, okay. All this is combining a lot. So, I mean, if you're a coach, well, you're going to say that on this side, you have to be careful of Hazard. On this side, I mean, you should just cut the connection to this whole thing because these guys are combining a lot and creating danger. And you see in particular that this guy is creating much more danger than this guy, right? Because he's combining with this, he's combining with him, and this figure. Okay, so this is a bit for the anecdote, of course, but if you think about it, I think that Hawkes processes, they are quite well adapted for this problem. They're very natural. And yeah, you can find some kind of funny function like this. We see that, yeah, Azpilicueta, Kante, and Victor Moses, you see that what is interesting that if you look at Azpilicueta, Kante, and Moses, if you just look at these basic statistics, the figures are small. But if you look at the more involved statistics, the figures become high. Yes?
I missed the point. From how many matches you computed the statistics?
So we need, I mean, we said that we make the statistics with 11, 12 games. Well,
11, 12
we need 11, 12 games. I mean, the needed game, I mean, it's a very good question. So what we did is that we did the experience on this with this algo. simulating random games and see how many games, we need to be able to estimate the parameter reasonably. And we need at least 11, 12, which is an issue because it's not often that you have the same, the same
Yes,
players.
and it's interesting, of course, to measure the if statistics change as the sample change.
Yeah,
no?
it's right.
If you pass from 100 games to games,
Yeah,
change, you know?
yeah. So according to the Monte Carlo, with 12 games, you're supposed to be more or less converged.
Okay.
But yeah, I mean, it's still, I agree with you. It's tricky because the dimension is high. So
You could also model the danger against their own team.
yes, we can. Yeah, how bad you are.
No, and then,
You
of
can-
course, then the defender, I mean, Courtois will have
Yeah.
more chances to do something stupid.
Yeah, exactly. I mean, we put that as a conclusion. Like you can say, like if you touch the ball, how dangerous you are for your own team. You can do that. So it's a bit anecdote, but as I was saying, the Hawks processes they are used in many different fields, and they're quite easy to use once you have the algos. And they are nicely interpreted, so I think that's why it goes.
You said what positions those players have?
Yes, so they are like this. This is their position. Right? So this is the goalkeeper here, and they are like this is the average position over the games that we have. This is the average position.
Oh, okay. Thank you.
And I'm gonna stop here. Thank you very much.
Okay, so are there questions, comments?
The alpha in the power law, the alpha equal 1/2, this has been estimated from price claim.
Actually, it's estimated from the market impact curve.
Market impact.
Yeah, from the market impact curve, and some people like Jean-Philippe and so Michaud and so on, they have arguments that are like physical arguments saying that alpha should be equal to 1/2 for some kind of physical argument. But it's more like estimated from the market impact curve. The caveat of that is that market impact curve is extremely noisy, so you cannot like not extremely reliable. But you know that the order of magnitude should be not too far from that.
The market impact curve where the underlying variable is the price. That's what.
Yeah. Absolutely. No, sorry.
If you were to do that, to take in considering another like exogenous variable that people describe as
like the flows or something like that.
exactly,
Yeah.
you may get another alpha.
Yeah.
No, actually, you just have to estimate the alpha for that kind of variable. So to get the market impact for that kind of.
Absolutely.
Okay. That's good.
Any comments? Answer?
First, wondering about, some processes have some embedding properties. So when you look at a restriction, it still follows the same type of process.
Yeah.
So in the case of interacting players, if you have like a changing team,
Yeah.
are there processes, I mean, maybe hooks or maybe not, but where you could look at one game as looking at a subset, but it would still be not consistent across.
So you know what we did is so actually we just took in the end statistics on when the tactic was the same without taking care of the players. And and then we say, okay, the guy who's like the most often here in this version, and so we swap that, kind of assuming what you're saying. So, but I'm not sure maybe it's true actually for also. I mean, we have to formalize that. I mean, in a better way. It's a good point that we should think about it. This is exactly what we need to be able to glue like stuff together. The thing is that we rely a lot on this estimation method. That is really like the Hawks process.
Just for fun, can you make this for two teams of the same guy, of the same coach?
Oh, yeah,
I think about Guardiola,
Of
the
course.
City and Barcelona. Does the graph
This will be
the
fun.
same
How effective he is.
This will be fun.
because of Guardiola?
So, it would be fun. And you can do it with Paris Saint-Germain. You look at the number of the players before they play in Paris Saint-Germain and when they play in Paris Saint-Germain, it's going to drop. You can do good thing. Yeah, it's a good idea. Good idea.
And so you can work also in the company to see who should be fired.
There will be a strike.
Very good. Thank you, boss.
Thank you.